In 1998, astronomers using the automatic plate measuring facility in the UK were scanning the sky. They cataloged objects. One of them, a faint point of light in the constellation Lynx, was labeled APM 8279 5255. For years, it was just another entry in a database. It was a quasar, a bright galactic core powered by a supermassive black hole. But in 2015, studies revealed something staggering. The object was being gravitationally lensed by a foreground galaxy. This lensing magnified it, allowing us to see details we otherwise couldn't. What we saw made no sense. The central black hole powering this quasar weighed 21 billion times the mass of our sun, a cloud of water vapor 100,000 times the mass of the sun, and containing 140 trillion times the water in all of Earth's oceans was swirling around it. The problem was not just its size. It was its age. We see this quasar as it was 12 billion years ago when the universe was young. Our models of how black holes grow are based on a process called accretion. Matter falls in, heats up, and glows. This glow creates radiation pressure that pushes other matter away. There is a physical limit to how fast a black hole can feed without choking itself off. This is called the Eddington limit. To reach 21 billion solar masses so early in the universe's history, APM 8279 5255 would have had to eat constantly, at a rate far exceeding this limit. It had to break the rule. This object was not an outlier. It was a sign. The universe is filled with objects so massive, so old, or so strange that they push our theories to the breaking point. They are the anomalies, the cosmic monsters that tell us our understanding of physics is incomplete. Number 20, TON 618, is a black hole that shouldn't be there. TON 618 has a mass of 66 billion suns. If it sat where our sun is, its event horizon, the point of no return, would swallow every planet all the way out past Neptune and into the Kuiper belt. The entire solar system would fit inside it thousands of times over. The light from its accretion disk, the swirling gas it is actively eating, shines with the power of 140 trillion suns. It is one of the brightest objects in the known universe. It is 10.4 billion light years away. It was first spotted in 1957 at the Tenancintla Observatory in Mexico. At the time, they couldn't tell what it was. On photographic plates, it looked like a faint blue star in the constellation Canes Venatici. It was entry 618 in the Tenancintla catalog, hence the name. For over a decade, that is all it was. A mystery star. Then, in the 1970s, radio telescopes detected signals from it. This meant it wasn't a star. It was a quasar. But its true nature was still hidden. The real shock came much later, when we could finally measure its mass. Astronomers did this by observing the gas clouds orbiting it. Just as we can calculate the sun's mass by the speed of Earth's orbit, they could calculate the black hole's mass by the speed of the gas. The gas was moving incredibly fast at speeds up to 7,000 kilometers per second. Only a colossal gravitational pull could hold on to gas moving that quickly. The final number was 66 billion solar masses. This number breaks our theories of black hole formation. There are two main ways we think supermassive black holes form. The first is that a large star, many times the mass of our sun, dies and collapses into a stellar mass black hole. Over billions of years, it merges with other black holes and accretes gas, slowly growing larger. The second theory is direct collapse. In the early universe, huge clouds of pristine gas could have collapsed directly into a massive black hole, skipping the star phase entirely. These seeds would be much larger, maybe 100,000 solar masses. Neither model can easily explain TON 618. We see it as it was 10.4 billion years ago. The universe was only about 3.4 billion years old. Starting from a stellar mass black hole, there simply has not been enough time for it to grow that big, even if it was eating as fast as physics allows, right at the Eddington limit. The direct collapse model helps by giving it a bigger head start, but even a 100,000 solar mass seed would need to accrete matter at an impossible rate. It would have to have been surrounded by an impossibly dense and constant supply of gas, and it would have had to consume it in a way that defies our understanding of accretion physics. Some theories propose super Eddington accretion, where the black hole somehow funnels gas in so efficiently that it overcomes the outward radiation pressure. But we don't know how that would work on such a sustained, massive scale. TON 618 suggests that either our timelines are wrong, or there is a third unknown mechanism for creating monster black holes in the early universe, a mechanism we have not even imagined yet. Number 19, the Hercules-Corona Borealis Great Wall is a structure too big to exist. It is 10 billion light-years across. This is more than 1/10 the diameter of the entire observable universe. If you could travel at the speed of light, it would take you 10 billion years to cross it. The structure is a vast filament, a concentration of galaxy clusters and gas, all held together by gravity. It is the single largest known object in the cosmos. Nothing else comes close. Its existence is a direct challenge to a fundamental principle of modern cosmology. It was discovered in 2013. A team of astronomers led by Istvan Horvath was not looking for a giant structure. They were studying gamma-ray bursts, or GRBs. GRBs are the most powerful explosions in the universe, thought to be caused by massive stars collapsing into black holes or neutron stars merging. They are so bright they can be seen from billions of light years away. Because they happen in galaxies, they can be used as markers to map the large-scale structure of the universe, like pins on a cosmic map. The team analyzed a database of GRBs from the Swift Gamma Ray Burst mission satellite. They noticed something odd. In a specific patch of the sky, in the direction of the constellations Hercules and Corona Borealis, there was a significant clumping of GRBs. The bursts were concentrated at a similar distance from us, about 10 billion light-years. This suggested they were all part of the same enormous system. The statistical analysis showed this was not a random coincidence. The probability of this many GRBs clustering by chance was incredibly low. The problem this creates is with the cosmological principle. This is a core assumption in our models of the universe, going back to Einstein. It states that, on a large enough scale, the universe is homogeneous and isotropic. That means it is basically the same everywhere, with matter distributed evenly. There should be no special places. Of course, on small scales, we see clumps, stars form in galaxies, galaxies form in clusters, but as you zoom out, these variations should smooth out. The universe should look like a uniform fog. Based on this principle, physicists calculated a theoretical maximum size for any structure. Any object larger than this would violate the assumption of homogeneity. That size is about 1.2 billion light-years. The Hercules-Corona Borealis Great Wall is almost 10 times larger than this limit. It means the universe is not as smooth as we thought. A structure this big suggests that the processes that formed the universe were not uniform. There were vast preferential directions and densities that our models do not account for. There is debate about the Great Wall's existence. Some scientists argue that using GRBs as tracers is not reliable. Perhaps there is a bias in how we detect them, making them appear clustered when they are not. Others suggest that the statistical methods used were flawed, but the team that discovered it stands by their data. If the Great Wall is real, it forces us to question the cosmological principle, and if that principle falls, many of our calculations about the universe's age, expansion, and ultimate fate may need to be revised. It suggests that our map of the cosmos is not just incomplete, but fundamentally drawn on the wrong kind of paper. Number 18, R136A1, is a star that should have blown itself apart. This star is 265 times the mass of our sun. It is also the most luminous star known, shining with nearly 9 million times the sun's brightness. If it replaced our sun, it would outshine it as much as the sun outshines the moon. Its surface temperature is over 50,000 Kelvin, 9 times hotter than the sun. It is located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 163,000 light years away. The star sits in the heart of the R136 star cluster, an incredibly dense and chaotic stellar nursery. For a long time, astronomers thought the bright light from the center of this cluster was a single supermassive object. But in 1985, using a technique called speckle interferometry, they were able to resolve the core into several individual stars. Even so, the technology wasn't good enough to see them clearly. It was the Hubble Space Telescope that finally gave us a clear view. The existence of R136A1 is a major problem for stellar formation and evolution theories. For decades, there was a widely accepted theoretical upper limit on the mass of a star. This was thought to be around 150 solar masses. This limit, known as the Eddington limit for stars, is based on a simple balance of forces. A star is a constant battle between gravity trying to crush it and the outward pressure of radiation from nuclear fusion trying to blow it apart. The more massive a star is, the hotter and faster it burns. A more massive star produces more radiation. At around 150 solar masses, the theory went, the outward radiation pressure would become so intense that it would overcome gravity. The star would blow off its outer layers, preventing it from ever growing larger. It would effectively regulate its own size. R136A1 at 265 solar masses is far beyond this limit. It should not be stable. The radiation pressure at its core should be so immense that it should have torn itself to shreds long ago. How did it form, and how is it still holding itself together? One theory is that it did not form this way. It might have been born from the merger of several smaller, but still massive stars. In the crowded center of the R136 cluster, stellar collisions and mergers are much more common than in a quiet neighborhood like ours. 100 solar mass stars could have collided and merged to form a single unstable giant. Even if it formed from a merger, its lifespan will be incredibly short. While our sun will live for about 10 billion years, a star like R136-1 will burn through its fuel in only 2 or 3 million years. It is living on borrowed time. It loses mass at a furious rate, ejecting a powerful stellar wind that is equivalent to losing the entire mass of the Earth every few weeks. Studying this star is a race against time. It is expected to end its life in a spectacular hypernova explosion, an event far more powerful than a typical supernova. It will leave behind a black hole, but its very existence, however brief, tells us that our understanding of the upper limits of stars was wrong. There are processes at work in the universe that can build stars far bigger than we thought possible. Number 17, the Methuselah star is older than the universe. The star is officially named HD 140,283. It is located about 190 light years from Earth in the constellation Libra. It is a subgiant star, metal poor, and moving at an incredible speed of 1.3 million kilometers per hour. We can see it with a pair of binoculars, but what makes this star so confounding is its age. Initial estimates made in the early 2000s put its age at 16 billion years. This is a problem. A huge problem. The currently accepted age of the universe based on observations of the cosmic microwave background by the Planck satellite and other missions is 13.8 billion years. A star cannot be older than the universe it exists in. It is a logical impossibility. The discovery was so bizarre that it was met with intense skepticism. The initial reaction was that the measurements must be wrong. So, astronomers went back to work. A team led by Howard Bond used the Hubble Space Telescope's fine guidance sensors to make extremely precise measurements of the star's distance. Knowing the exact distance is crucial for determining a star's luminosity, or its true brightness. Once you know its brightness, you can model its evolution and calculate its age. The new parallax measurements were much more accurate. They also refined the models of stellar nucleosynthesis, accounting for how a star with very few heavy elements like this one would burn its fuel. They also considered that the star likely had more oxygen than previously assumed, which would also affect its life cycle. After all these corrections, the team announced a new revised age for HD 140,283 in 2013. The new age was 14.46 billion years. This was better, but still older than the universe. However, this new number came with an uncertainty of plus or minus 0.8 billion years. This uncertainty is key. It means the star's actual age could be as low as 13.66 billion years. This value is just within the age of the universe. It is an incredibly close shave. The star would have to have formed almost immediately after the Big Bang, making it one of the very first stars to exist, a true second-generation star formed from the ashes of the very first primordial stars. While the uncertainty allows the star's age to just barely fit within our cosmic timeline, it is still an uncomfortable fit. It pushes the boundaries of our models for how quickly the first stars could form. The universe needed time to cool down after the Big Bang for gas to coalesce and ignite into stars, for HD 140,283 to be as old as it is. This process must have happened extremely rapidly. The Methuselah star remains a puzzle. It could be that there is still some unknown factor in our models of stellar evolution that we are missing. It could be that our measurement of the universe's expansion rate, the Hubble constant, needs a slight adjustment, which would in turn change the calculated age of the universe. Or it could be that our understanding of dark energy, the mysterious force accelerating cosmic expansion, is incomplete. The star acts as a firm physical anchor. Our theories about the cosmos must be able to explain it. Right now, they can, but only just barely. Number 16, El Gordo is a galactic collision on an impossible scale. And El Gordo means the fat one in Spanish. Its official name is ACT CL J0102 4915. It is a galaxy cluster, or more accurately, two galaxy clusters in the process of a titanic collision. It is located more than 7 billion light-years away. Its total mass is estimated to be 3 quadrillion times the mass of our sun. That is 3,000 trillion suns. It is the most massive galaxy cluster known to exist in the distant or early universe. It was discovered in 2012 using data from the Atacama Cosmology Telescope in Chile, and then followed up with observations from NASA's Chandra, the 10th Ray Observatory, and the European Southern Observatory's Very Large Telescope. What the astronomers saw was astonishing. Two massive clusters were smashing into each other at a speed of several million kilometers per hour. The collision was generating a shock wave of superheated gas, visible in X-rays. The problem with El Gordo is its sheer mass at such an early point in cosmic history. We are seeing it as it was when the universe was about half its current age. According to the standard model of cosmology called lambda CDM, structures in the universe grow hierarchically. Small things form first, like stars and small galaxies. Over billions of years, gravity pulls these smaller structures together to form larger and larger ones, galaxy groups, then clusters, and finally superclusters. It is a slow bottom-up process. A monster like El Gordo should not exist at that time. It is too big, too early. The standard model predicts that clusters of this immense size should be exceedingly rare in the early universe. Finding one is like finding a fully grown redwood tree in a field where you only expected to see saplings. It suggests that the process of structure formation might be faster than we think. The collision itself also presents a puzzle. When the two clusters collided, the normal matter, the hot gas that makes up most of a cluster's visible mass, crashed into itself and slowed down due to friction. We can see this glowing gas with X-ray telescopes. However, the dark matter, which makes up the bulk of the cluster's mass, does not interact with normal matter or itself except through gravity. So the vast clouds of dark matter from each cluster passed right through each other, like ghosts. We can map the location of the dark matter by observing how its gravity bends the light from distant galaxies behind it, a phenomenon called gravitational lensing. When astronomers mapped the dark matter in El Gordo, they found that it was separated from the hot gas. This separation of dark and normal matter is strong evidence for the existence of dark matter. But the dynamics of the collision, the speed, and the mass involved are at the extreme edge of what our cosmological simulations can produce. El Gordo is a 1 in a billion type of object. Its existence strains the lambda CDM model. It might mean that the initial density fluctuations in the early universe were larger than we thought, providing the seeds for these giant structures to grow much more quickly. Number 15, the huge LQG is a cluster of quasars that defies homogeneity. The huge LQG, or huge large quasar group, is a collection of 73 quasars. It is so large that it takes 4 billion years to cross it at the speed of light. Its average size is about 1.6 billion light years, but its longest dimension stretches for 4 billion light years. It is located about 9 billion light years from Earth. At the time of its discovery in 2013, it was the largest known structure in the universe, a title later taken by the Hercules-Corona Borealis Great Wall. A team from the University of Central Lancashire in the UK, led by Roger Clowes, discovered it. They were using data from the Sloan Digital Sky Survey, a major project that has mapped a huge portion of the night sky. They were looking for large-scale structures by mapping the distribution of quasars. Quasars are the intensely bright cores of distant young galaxies. Because they are so bright, they can be used to trace the distribution of matter over vast cosmic distances. The team found a massive overdensity of quasars in one region of the sky, all at roughly the same distance from us. This meant they were part of a single, gravitationally associated structure. Like the Hercules-Corona Borealis Great Wall, the huge LQG is a major problem for the cosmological principle. As mentioned before, this principle assumes that the universe is uniform on large scales. Based on this, there is a theoretical size limit for any cosmic structure, which is around 1.2 billion light years. The huge LQG at 4 billion light years in its longest dimension shatters this limit. It is simply too big to be consistent with our standard model of cosmology. A structure this large would not have had time to form in a universe that is supposed to be smooth and even. It implies that matter in the early universe was far lumpier than predicted. The existence of the huge LQG is controversial. Some scientists have questioned the statistical methods used to identify it. They argue that the algorithm used to find clusters of quasars might be finding patterns in the data that are not physically real. It could be a chance alignment of smaller, unrelated groups. One study in 2016 reanalyzed the data and concluded that the huge LQG was not a real structure and was compatible with a random distribution of quasars. However, the original discovery team has defended their findings. They point out that the orientation of the quasars within the group seems to be aligned, suggesting they are part of a coherent system. The debate is ongoing. If the huge LQG is a real gravitationally bound structure, it would mean the cosmological principle, a bedrock of our understanding of the universe for almost a century, is wrong. It would force a fundamental rethink of our theories of cosmic evolution. It would mean that the universe we live in is not as simple or as uniform as we have long assumed. It could have vast, continent-sized structures that are a relic of a far more chaotic and lumpy beginning than our theories currently allow. Number 14, GNZ11, is a galaxy too bright and too old for its time. GNZ11 is a galaxy in the constellation Ursa Major. We see it as it was 13.4 billion years ago. This means the light we are seeing now left that galaxy just 400 million years after the Big Bang. At the time of its discovery in 2016, it was the oldest and most distant galaxy ever observed. It is a tiny galaxy, only about 1/25th the size of our Milky Way, and with only 1% of its mass in stars. But its existence at that early time is what is so puzzling. A team of astronomers discovered it using the Hubble Space Telescope. They were conducting a survey of very distant galaxies. Using Hubble's spectrograph, they were able to measure the galaxy's redshift, which is a measure of how much its light has been stretched by the expansion of the universe. The higher the redshift, the farther away and older the object is. GNZ11 had a redshift of z equals 11.1, which was a new record. The problem with GNZ11 is its brightness. Despite its small size, it is surprisingly luminous. It is forming stars at a furious rate, about 20 times faster than the Milky Way does today. This rapid star formation makes it bright enough for us to see, even from across the entire observable universe. But our models of early galaxy formation did not predict that galaxies could ramp up star production so quickly. The first 400 million years of the universe were supposed to be a time of slow, gradual buildup. The first stars, known as population the third stars, would have formed from pure hydrogen and helium. These stars would have been massive and short-lived, exploding as supernovae and seeding the surrounding gas with the first heavy elements, or metals, as astronomers call them. Only after this seeding process could the next generation of stars and the first small galaxies begin to form. GNZ11 appears to be a well-established, chemically enriched galaxy, churning out stars at a mature rate. It seems to have skipped its cosmic childhood and jumped straight to adolescence. How did it get so big and bright so fast? One possibility is that our models of early star formation are too slow. Perhaps the first stars were able to form and enrich their surroundings much more efficiently than we thought. Another idea is that GNZ11 contains a supermassive black hole at its center that is accreting matter and powering a quasar. This would add to the galaxy's brightness, but it also creates another problem. How did a supermassive black hole form so early? It is the same timing problem we see with quasars like TON 618, but even more extreme because GNZ11 is so much older. The James Webb Space Telescope JUICE is now studying GNZ11 and other galaxies like it in even greater detail. Early results from JUICE have confirmed the existence of many surprisingly bright and massive galaxies in the early universe, suggesting that GNZ11 was not a fluke. This growing collection of impossible early galaxies is putting serious pressure on the standard model of cosmology. It suggests that the process of galaxy formation was not a slow bottom-up process, but a rapid top-down one, with massive structures forming much earlier than our theories predict. Number 13, PSR J0740/6, 620 is a neutron star on the brink of collapse. The PSR J0740/46, 1620 is a neutron star. It is a pulsar, meaning it is rapidly rotating and emits beams of radiation that sweep across space like a lighthouse. This particular pulsar is located about 4,600 light-years away. It is part of a binary system orbiting a white dwarf companion. The neutron star itself is incredibly dense. A single teaspoon of its material would weigh billions of tons. But what makes it a rule breaker is its mass. In 2019, astronomers measured its mass to be 2.14 times that of our Sun. This makes it the most massive neutron star ever found. The measurement was made using a phenomenon called Shapiro delay. The neutron star and its white dwarf companion orbit each other edge-on from our perspective. This means that once per orbit, the light from the pulsar has to pass very close to the white dwarf on its way to Earth. The strong gravity of the white dwarf warps space-time, causing the pulsar's signal to travel a slightly longer path and arrive a few millionths of a second later than expected. By precisely measuring this tiny delay, astronomers can calculate the mass of the white dwarf. And once they know the white dwarf's mass, they can use the orbital dynamics of the system to calculate the mass of the neutron star. The result was a surprisingly high 2.14 solar masses. This mass pushes our understanding of nuclear physics to its absolute limit. A neutron star is what is left after a massive star goes supernova. The core collapses under its own gravity, crushing protons and electrons together to form neutrons. The entire star, with more mass than the sun, is squeezed into a sphere only about 20 kilometers in diameter. What stops it from collapsing further into a black hole is a quantum mechanical principle called neutron degeneracy pressure. The neutrons resist being squeezed any closer together, but there is a limit to how much mass this pressure can support. This is called the Tolman-Oppenheimer-Volkoff-Tov limit. If a neutron star accretes too much matter, say from its binary companion, and crosses this limit, gravity will win. Neutron degeneracy pressure will fail, and the star will instantly collapse into a black hole. The problem is, we do not know the exact value of the Tovey limit. It depends on the equation of state of the matter inside the neutron star. We do not know how matter behaves under such extreme densities. It is a state of matter we cannot create in a lab on Earth. Is it just a sea of neutrons, or do the neutrons themselves break down into their constituent quarks, forming a quark star? Different equations of state predict different maximum masses. PSR J07 46,620 at 2.14 solar masses rules out many of the softer equations of state, those that predict a lower maximum mass. It tells us that the matter inside a neutron star must be extremely stiff and resistant to compression. It forces physicists to reconsider their models of exotic matter. The star is living right on the edge. Any further increase in its mass could push it over the brink. It is a natural laboratory for studying the most extreme physics in the universe. Its existence is a crucial clue in the quest to understand how matter behaves when it is crushed to the breaking point by gravity. Number 12, NGC 1277, has a black hole that is far too big for its galaxy. NGC 1277 is a small, compact, lenticular galaxy in the Perseus cluster about 220 million light-years away. It is an old galaxy full of ancient stars with very little new star formation. From the outside, it looks unremarkable, but at its heart lies a monster that makes no sense. In 2012, a team of astronomers measured the mass of its central supermassive black hole. They found it was 17 billion times the mass of the Sun. This in itself is a very large black hole, but not a record breaker. The problem is not its absolute mass, but its mass relative to its host galaxy. The black hole in NGC 1277 accounts for 14% of the total mass of the galaxy. In some estimates, it is as high as 59% of the mass of the galaxy's central bulge. This is completely out of line with what we see in almost every other galaxy. For years, astronomers have observed a tight correlation between the mass of a galaxy's central black hole and the mass of its central bulge of stars. Typically, the black hole's mass is only about 0.1% of the bulge mass. The Milky Way's black hole, Sagittarius A, is about 4 million solar masses, while our galaxy's bulge is billions of solar masses. This correlation suggested that galaxies and their central black holes grow together in a process of coevolution. The galaxy feeds the black hole, and the black hole, through jets and radiation, regulates the galaxy's star formation. They grow in lockstep. NGC 1277 completely violates this relationship. Its black hole is over 100 times more massive than it should be for a galaxy of its size. It is a head on a tiny body. This discovery throws a wrench into our theories of galaxy evolution. How could such a small galaxy grow such an enormous black hole? Or, from another perspective, why did the galaxy stop growing while its black hole continued to balloon in size? One theory is that NGC 1277 is a stripped galaxy. It might have once been a much larger galaxy that had a close encounter with another, larger galaxy in the dense Perseus cluster. The gravitational interaction could have stripped away most of its outer stars, leaving behind only the dense central bulge and its oversized black hole. It is a relic of a much larger parent galaxy. Another idea is that NGC 1277 and its black hole are a pristine remnant from the early universe. Perhaps in the very early cosmos, massive black holes formed first, and then the galaxies grew around them. In most cases, the galaxy eventually caught up in size, but NGC 1277 might be a case where the galaxy's growth was stunted for some reason, leaving the primordial oversized black hole exposed. The galaxy is a puzzle. It is a challenge to the idea of peaceful coevolution between galaxies and black holes. It suggests that their relationship might be more complex and violent than we thought, shaped by chaotic interactions and ancient conditions that we are only just beginning to understand. Number 11. The Smith Cloud is a gas cloud that survived a galactic journey. The Smith Cloud is a colossal cloud of hydrogen gas. It is shaped like a comet, about 11,000 light-years long and 2,500 light-years wide. It contains enough gas to form 1,000,000 stars like our sun. It is currently crashing into the disk of our own Milky Way galaxy at a speed of over 300 kilometers per second. It is expected to fully merge with our galaxy in about 30 million years, triggering a burst of star formation. The cloud was discovered in 1963 by a radio astronomy student named Gail Smith. She detected its radio signals using the Green Bank telescope. For decades, its origin was a mystery. We knew it was on a collision course with us, but we did not know where it came from. Was it a failed dwarf galaxy that never managed to form stars? Or was it just a loose clump of gas pulled from another galaxy? The real puzzle emerged in 2016. A team of astronomers using the Hubble Space Telescope was able to measure the chemical composition of the cloud. They did this by observing the light from distant galaxies that passed through the cloud. The gas in the cloud absorbed some of this light, leaving a chemical fingerprint. What they found was that the Smith Cloud is not made of pristine primordial gas from outside our galaxy. It is rich in heavy elements like sulfur. The abundance of these elements is almost identical to the abundance found in the outer disk of the Milky Way. This discovery meant only one thing: the Smith Cloud was born inside the Milky Way. It was ejected from our galaxy's disk, traveled far out into the galactic halo, and is now falling back in. It is a galactic boomerang. This solves the origin mystery, but it creates a new, much harder problem. How did it survive the journey? A cloud of gas with no stars to hold it together with gravity should be very fragile. As it was launched out of the Milky Way's disk, it would have had to push through the hot, tenuous gas of the galactic halo. This process should have been like a smoke ring hitting a wall. The cloud should have been shredded and dissipated into the halo gas millions of years ago. It should not exist as a coherent, massive structure today. The fact that the Smith Cloud is still intact is a major challenge to our models of gas dynamics in galaxies. One theory is that the cloud is encased in a protective shell of dark matter. A dark matter halo could provide the extra gravity needed to hold the gas cloud together as it plowed through the halo. If this is true, the Smith Cloud would be a unique object, a dark matter-dominated gas cloud with no stars. It would be a dark galaxy that failed to ignite. Another possibility is that magnetic fields are playing a role. The cloud might have a strong internal magnetic field that is helping to contain the gas and protect it from being stripped away. You know, whatever the mechanism, the Smith Cloud's survival is a mystery. It is a ghost from our galaxy's past returning to tell us that we are missing something important about the complex interplay of gas, gravity, and dark matter that governs the life of a galaxy. Number 10, Stephenson, 2 to 18, is a star so large it defies belief. Stephenson 2 to 18 is a red supergiant star. It is located in the open star cluster Stephenson 2, about 20,000 light-years away in the constellation Scutum. It is the largest star known by physical size. Its estimated radius is 2,150 times that of our Sun. If it were placed at the center of our solar system, its surface would extend out past the orbit of Saturn. Light would take over 9 hours to travel around its circumference. It is a true behemoth. The star was discovered by the American astronomer Charles Stephenson in 1990. He identified it as a member of a newly discovered cluster of red supergiants. But its true size was not appreciated until much later. Measuring the size of a distant star is incredibly difficult. They are just points of light. Even in the most powerful telescopes, astronomers have to estimate their size based on their temperature and luminosity. In 2020, a new study used better data to calculate the luminosity of Stephenson 2 to 18, and from that they derived its staggering radius. The sheer physical size of Stephenson 2 to 18 pushes the boundaries of our stellar evolution models. A star this large is in a very late and unstable stage of its life. It has swelled up to an enormous size, and its outer layers are only weakly held on by gravity. It is shedding mass at a prodigious rate. The physics of how a star can remain stable at this extreme size is not well understood. There are also significant uncertainties in the measurement. The star is heavily obscured by interstellar dust, which makes it hard to determine its exact temperature and brightness. The distance to the Stephenson 2 cluster is also not known with perfect accuracy. Some astronomers argue that the star's size might be overestimated. It could be smaller and cooler, or larger and hotter than the current best estimate. Even with these uncertainties, it is undeniably one of the largest stars ever found. Its existence raises questions about the late stages of evolution for the most massive stars. Our models predict that as massive stars evolve, they lose a significant amount of their mass through powerful stellar winds. This mass loss should limit how large they can physically swell up in their final stages. Stephenson 2 to 18 and other red supergiants like UY Scuti seem to be larger than these models would predict. This suggests that our understanding of mass loss in evolved stars might be incomplete. Perhaps the process is less efficient than we thought, allowing stars to retain more of their mass and inflate to even greater sizes before they finally explode as supernovae. Stephenson 2 to 18 is a laboratory for studying the last dramatic moments in the life of a massive star. Its colossal size is a testament to the extreme physical processes that can occur in the universe, processes that we are still struggling to fully comprehend. Number 9, the Eridanus supervoid is an emptiness that shouldn't be so cold. The Eridanus supervoid is a vast, empty region of space. It is located in the direction of the constellation Eridanus. It is about 1.8 billion light-years in diameter, making it one of the largest structures ever discovered. But what defines it is not what is in it, but what is not. This region has far fewer galaxies, and therefore far less matter than the average region of the universe. It is a colossal cosmic desert. Its existence was first hinted at in 2004. Scientists analyzing data from the Wilkinson Microwave Anisotropy Probe WMAP satellite noticed an unusually large and cold spot in the cosmic microwave background CMB. The CMB is the faint afterglow of the Big Bang, a thermal radiation that fills the entire universe. It is remarkably uniform in temperature, but it has tiny fluctuations. These fluctuations correspond to the initial density variations in the early universe that seeded the formation of all the structures we see today. The spot in Eridanus was significantly colder than the average CMB temperature. It became known as the CMB cold spot. Initially, no one knew what to make of it. Was it just a statistical fluke, or was it a sign of new physics, perhaps a cosmic defect, or even the signature of a collision with another universe? In 2007, astronomers pointed radio telescopes at that patch of sky. They mapped the distribution of galaxies in that direction, and found that the cold spot corresponded perfectly with a huge underdensity of galaxies. They had found the Eridana supervoid. This discovery explained part of the mystery. The emptiness of the void could make the CMB light passing through it appear colder. This is a phenomenon called the integrated Sachs-Wolf ISW effect. As light enters a void, it gains energy a blue shift as it falls into the shallow gravitational well. As the universe expands, the void stretches and becomes even shallower. So as the light climbs back out of the well, it loses less energy than it gained on the way in. The net effect is that the light should appear slightly hotter, not colder. However, due to the effects of dark energy, which accelerates the expansion, the opposite can happen, leading to a slight cooling. Here is the problem. While the ISW effect can explain a cold spot caused by a void, the Eridana supervoid is not big or empty enough to explain the full extent of the coldness we observe. The observed temperature dip is much larger than the ISW effect from this void can account for. The standard model of cosmology cannot explain the discrepancy. This has led to a lot of speculation. One possibility is that there is something else going on inside the void that we cannot see. Another is that the void is just a red herring, a chance alignment with a truly anomalous cold spot in the CMB. Some more exotic theories suggest that the cold spot could be evidence for a multiverse. It could be a bruise left on our universe from an ancient collision with another bubble universe. This is highly speculative, but the fact that such theories are being seriously considered shows how big of a puzzle the cold spot is. It is a genuine anomaly in our best map of the early universe, a cold, empty place that challenges our most fundamental cosmological model. Number 8, the Great Attractor is a gravitational anomaly we can't see. The Great Attractor is a region of space about 200 million light-years from us. It is not an object, but a location. It is a place where gravity is so concentrated that it is pulling our own Milky Way galaxy, the Andromeda galaxy, and the entire Laniakea supercluster of galaxies towards it. We are moving towards it at a speed of over 600 kilometers per second, which is about 2.2 million kilometers per hour. The first hints of its existence came in the 1970s. Astronomers were measuring the velocities of galaxies relative to the cosmic microwave background, which serves as a stationary reference frame for the universe. They expected to see galaxies moving away from each other due to the Hubble expansion, with some small random motions on top. But they found a large-scale, coherent flow. Entire clusters of galaxies seemed to be streaming in a particular direction, towards the constellations of Triangulum Australe and Norma. There had to be a huge, unseen concentration of mass in that direction, pulling everything towards it. They called it the Great Attractor. The problem was we could not see what it was. This region of space lies directly behind the plane of our own Milky Way galaxy. This area is called the Zone of Avoidance because the dense gas, dust, and stars of our galactic disk block our view of what lies beyond. It is like trying to see a mountain through a thick fog. This is, for decades, the nature of the Great Attractor remained a mystery. In the 1980s and 90s, astronomers began to use radio and infrared telescopes, which can peer through the dust more effectively. And they discovered the Norma cluster, a large galaxy cluster right in the suspected location of the Great Attractor. This seemed to be the answer, but when they calculated the mass of the Norma cluster, it was not enough. It could only account for a fraction of the gravitational pull needed to explain the observed motion of our local group of galaxies. The mystery deepened. In 2016, a major survey using the Parkes radio telescope finally managed to map the galaxies behind the Milky Way in detail. This survey, called Wallaby, discovered hundreds of new galaxies. It revealed that the Great Attractor is not a single object, but a vast overdensity of galaxies, with the Norma Cluster at its core. But even with all these newly discovered galaxies, the total observed mass still falls short of what is needed to explain our motion. There is still a missing piece of the puzzle. The remaining gravitational pull might be coming from something even larger and more distant. The Shapley supercluster, a colossal collection of galaxy clusters, lies beyond the Great Attractor. Some of our motion is likely due to the pull of Shapley, but the exact contribution of each structure is still being debated. The Great Attractor is a perfect example of how difficult it is to map our cosmic neighborhood. It shows that even in our relatively nearby universe, there can be gravitational giants hiding in plain sight, their true nature obscured by the very galaxy we live in. Number 7. ULAS J132 plus 228 is a quasar from the cosmic dawn. ULAS J1342 plus 9, 128 is a quasar. At its heart is a supermassive black hole with a mass of 800 million suns. It was discovered in 2017. What makes it extraordinary is its age. We are seeing this quasar as it was only 690 million years after the Big Bang. This was during a period known as the Epoch of Ryanization, when the first stars and galaxies were just beginning to light up the universe and burn away the neutral hydrogen fog that had filled space since the cosmic dark ages. Finding a quasar this old is a monumental achievement. It is also a monumental problem for astrophysics. The central black hole is 800 million solar masses. To grow a black hole this large, this quickly, is a feat that our current models struggle to explain. It is like meeting a fully grown adult who claims to be only 3 years old. Let's consider the timeline. The universe is 690 million years old. The first stars probably did not form until 100 to 200 million years after the Big Bang. Let's say one of the very first massive stars died and left behind a black hole of about 100 solar masses. To grow from 100 solar masses to 800 million solar masses in just a few hundred million years, this black hole seed would have had to accrete matter continuously at its maximum possible rate, the Eddington limit. There is no room for error. It had to be eating as fast as physically possible without interruption from the moment it was born. This scenario is extremely unlikely. The early universe was a chaotic place, but finding a constant, perfectly tuned supply of gas to feed a black hole for that long is difficult to imagine. Any disruption, like a nearby supernova explosion, would have cut off the fuel supply and stopped its growth. This has forced scientists to consider more exotic formation scenarios. One idea is the direct collapse black hole. As mentioned before, this theory suggests that under the right conditions in the early universe, a massive cloud of primordial gas could have collapsed directly into a black hole of 10,000 to 100,000 solar masses, skipping the star phase. This would give the black hole a significant head start, making it easier to reach 800 million solar masses in the available time. Another possibility is that the early universe was populated by small, dense star clusters. The stars in these clusters could have collided and merged rapidly, forming a supermassive star that then collapsed into an intermediate mass black hole. This black hole could then have merged with others. The discovery of ULAS J1342 and 28 and other quasars from a similar epoch suggests that whatever the process was, it was efficient and common. These early monster black holes are not rare freaks. They seem to be a normal part of early cosmic evolution. This means our standard picture of slow, steady growth for black holes is likely wrong, at least for the first billion years of the universe's history. There was a fast track for building giants, and we are still trying to figure out what it was. Number 6, the impossible galaxy is a dead galaxy in a young universe. The galaxy is called ZF Cosmos 20115. It is a massive galaxy with about 3 times as many stars as our modern-day Milky Way. What makes it impossible is not just its size, but its state. It is a quiescent galaxy, meaning it has stopped forming stars. It is a red and dead galaxy full of old red stars, and we are seeing it as it was 12 billion years ago, when the universe was only 1.65 billion years old. It was discovered by a team of astronomers using data from the Keck Observatory in Hawaii. They were specifically looking for old, non-star forming galaxies in the early universe. According to our models of galaxy formation, they should not have found any. The early universe was a time of frenetic activity. Gas was plentiful, and galaxies should have been furiously forming new stars. A galaxy was not expected to run out of gas and ID until much later in cosmic history. Finding a massive dead galaxy like ZF Cosmos 20,115 at such an early epoch is a major contradiction. It implies that the galaxy must have formed all of its stars in an incredibly rapid and intense burst of star formation that happened even earlier and then shut down just as quickly. All of this must have happened within the first 1.5 billion years of the universe's existence. This timeline is extremely compressed. The galaxy had to accumulate a huge amount of gas, convert it all into stars at an unbelievable rate, and then somehow expel all of its remaining gas to quench any future star formation. Our simulations of galaxy evolution struggle to reproduce this life cycle. The feedback mechanisms we know of, like jets from a central supermassive black hole or winds from supernovae, are generally not thought to be powerful enough to shut down a massive galaxy so completely, so early on. The existence of this galaxy suggests that the processes that regulate galaxy growth and death can happen much faster and more violently than we previously thought. It challenges the standard hierarchical model of galaxy formation, which favors a more gradual assembly over billions of years. ZF Cosmos 20,115 looks like a modern, evolved galaxy that has been transported back in time. Since its discovery, the James Webb Space Telescope has found even more examples of these quiescent galaxies in the early universe. They are more common than expected. This growing collection of impossible dead galaxies is forcing a revision of our theories. It seems the early universe was capable of building and killing off massive galaxies on a timescale that our models are only beginning to grapple with. It paints a picture of a young cosmos that was far more efficient at assembling and evolving galaxies than we ever gave it credit for. Number 5, the Bullet Cluster provides smoking gun evidence for dark matter. The Bullet Cluster, officially 1E657-56, is another example of 2 galaxy clusters colliding. It is located about 3.7 billion light-years away. It is not rule-breaking because of its mass or age, but because of what the collision reveals about the nature of mass itself. It provides the most direct evidence we have for the existence of dark matter. The collision is happening at a blistering speed of 4,500 kilometers per second. Just like with El Gordo, the different components of the clusters behaved differently during the crash. The normal matter, which is mostly hot gas, from each cluster slammed into the other. This created a huge shockwave, which we can see in X-rays. This hot gas, which contains almost all of the cluster's normal baryonic mass, slowed down in the collision. It looks like a bullet-shaped cloud of gas, which gives the cluster its name. The stars within the galaxies of each cluster, being small and widely spaced, mostly passed right through each other without colliding. But the most interesting part is what happened to the dark matter. Since dark matter does not interact with normal matter or itself, except through gravity, the huge clouds of dark matter from each cluster pass straight through each other, just like the galaxies did. The result is a clear physical separation of the different types of mass. We can map the location of the normal matter by looking at the X-ray emitting gas. We can map the location of the total mass, both normal and dark, by looking at gravitational lensing. When we do this, we find that the vast majority of the mass is not where the hot gas is. The mass, detected by lensing, is located in 2 clumps on either side of the hot gas, exactly where the galaxies are. This means that most of the mass in the cluster is not the gas that we see. It is an invisible substance that passed through the collision unscathed. This is the dark matter. This observation is a huge problem for alternative theories of gravity. Some theories, like modified Newtonian dynamics MOND, try to explain the missing mass problem in galaxies not by proposing a new type of particle dark matter, but by modifying the laws of gravity over large distances. In these theories, there is no dark matter. Gravity is just stronger than we think. The bullet cluster is a direct refutation of these simple MOND theories. If gravity were simply modified, the gravitational lensing signal, the mass should still be centered on the normal matter, the hot gas, because that is where most of the normal mass is. The fact that the center of mass is displaced from the center of normal matter is something these theories cannot explain without adding their own complex form of dark matter, defeating their original purpose. The bullet cluster shows us that dark matter is a real substance, not just an illusion created by our misunderstanding of gravity. It is a cosmic scale particle collider experiment that has separated dark matter from normal matter, allowing us to see its effects directly. Number 4, Westerland 1 to 26 is a hypergiant shedding its skin. Westerland 1 to 26 is a red hypergiant star in the star cluster Westerland 1, about 11,500 light-years from Earth. It is one of the largest stars known, with a radius estimated to be over 1,500 times that of the Sun. It is also surrounded by a strange and unexpected nebula of glowing gas. This star is in the very final stages of its life. It has swelled to enormous proportions and is extremely unstable. In 2013, astronomers studying it noticed something odd. The star was surrounded by a cloud of ionized hydrogen. This was strange because a cool star like a red hypergiant, with a surface temperature of only about 3,000 Kelvin, should not be hot enough to ionize the gas around it. Ionizing hydrogen requires high-energy ultraviolet radiation, something these stars do not produce much of. Then, in 2021, observations revealed an even more complex structure. The star is surrounded by a vast, glowing nebula of gas that it has ejected. The nebula is shaped like a torus or a ring, and it is huge, spanning several light years. This material was shed by the star in a series of eruptions over the past 10,000 years. The mystery is how this nebula was formed and how it is being lit up. The star seems to have undergone a dramatic change in its recent past. It may have gone through a yellow hypergiant phase, a hotter and more unstable period where it shed its outer layers. But even that does not fully explain the nebula's structure and ionization. One tantalizing theory is that the star is not alone. It might have a small, hot companion star orbiting it. This companion would be too dim to see next to the glare of the hypergiant, but its ultraviolet radiation could be responsible for lighting up the nebula. The companion could also have influenced the shape of the ejected material, forming the ring-like structure. Another possibility is that the star reignited in a way. It could have undergone a thermal pulse, a late-stage helium flash in its core, which temporarily made it much hotter and caused it to eject the material and ionize it. Westerland 1 to 26 is a puzzle that challenges our understanding of the final chaotic stages of massive stellar evolution. These stars are so rare and so short-lived that we have very few examples to study. Each one provides a crucial snapshot of a process that is key to understanding how heavy elements are created and recycled into the cosmos. The star is effectively shedding its skin before our eyes, and the process is far more complex and beautiful than our models had predicted. It is a dying giant that is refusing to go quietly. Number 3, HD 100,546b is a planet too big and too far away. HD 100,546b is an object orbiting the young star HD 100,546 about 335 light-years from Earth. It is either a giant exoplanet or a small brown dwarf, a failed star. What makes it a problem is its combination of size and location. It is estimated to be about 7 times the mass of Jupiter, and it orbits its star at a distance of 53 times the distance from the Earth to the Sun. That is almost twice as far out as Neptune orbits our Sun. It was discovered in 2013. Astronomers were studying the protoplanetary disk around the star HD 100,546. This is a disk of gas and dust where planets are actively forming. Using direct imaging techniques, they spotted a faint point of light embedded in the disk. It appeared to be a planet in the process of being born. The problem is how it got there. There are 2 main theories of how giant planets form. The first is core accretion. This is how we think Jupiter formed. A rocky core of about 10 Earth masses forms first. This core's gravity then becomes strong enough to rapidly pull in a huge amount of gas from the surrounding disk, forming a gas giant. The problem with this model for HD 100,546b is its distance from the star. At 53 AU, the protoplanetary disk is much less dense, and orbital times are very long. There is simply not enough material and not enough time for a core to grow large enough to trigger runaway gas accretion. Core accretion is not efficient that far out. The second theory is disk instability. In this model, a massive, unstable protoplanetary disk can fragment under its own gravity, with large clumps of gas collapsing directly to form a giant planet. This process is thought to work better in the outer regions of a disk. This seems like a good fit for HD 100,546b. However, the disk around HD 100,546 does not appear to be massive enough to be unstable in this way. So we have an object that is too far out to have formed by core accretion in a disk that is not massive enough for it to have formed by disk instability. Its existence is a direct challenge to our 2 primary models of planet formation. The situation is further complicated by its size. At 7 Jupiter masses, it is right on the borderline between a planet and a brown dwarf. It might not be a planet at all, but a failed star that formed alongside its larger companion star, like a binary system. But even this is problematic. Binary stars typically form closer together or much farther apart. Its orbit is in a strange intermediate zone. HD 100,546b is a system that breaks all the rules. It is a planet that shouldn't be where it is, or a brown dwarf in an orbit it shouldn't have. It tells us that our neat and tidy theories of how solar systems form are missing a crucial piece of the puzzle. There may be other unknown mechanisms for building giant worlds in the cold, distant regions of a stellar system. Number 2. The Phoenix Cluster is making too many stars. The Phoenix Cluster, officially SPT-CL J2344 4243, is a massive galaxy cluster located 5.7 billion light-years away. At the center of this cluster is a huge galaxy that is undergoing a truly monstrous burst of star formation. It is creating new stars at a rate of about 740 solar masses per year. For comparison, our Milky Way galaxy produces only about 1 or 2 new stars per year. This is the most extreme starburst ever seen in the center of a galaxy cluster. This intense activity is what breaks the rules. For years, astronomers have studied galaxy clusters and found that the massive central galaxies are almost always red and dead. They are filled with old stars and have very little new star formation. This is because the supermassive black hole at the center of the galaxy is thought to heat up the surrounding gas. The black hole pumps out energy through jets and radiation, which prevents the vast reservoir of hot gas in the cluster from cooling down and collapsing to form new stars. This process is called AGN feedback, and it was thought to be a universal mechanism for quenching star formation in cluster centers. The Phoenix Cluster is a blatant exception. Its central galaxy is surrounded by an enormous amount of hot gas, like all cluster center galaxies. But for some reason, the gas is cooling rapidly. Vast streams of gas are flowing towards the center of the galaxy and fueling the incredible starburst. This means that the central black hole, despite being very massive and active, is failing at its job. It is not able to stop the gas from cooling. This discovery, made in 2012, was a major shock. It showed that the AGN feedback process is not as simple or as universally effective as we thought. The balance between heating from the black hole and cooling of the gas is a delicate one. In the Phoenix cluster, the cooling is winning by a landslide. Why is this happening? We still do not know for sure. It could be that the black hole's feedback is intermittent. It might go through cycles of being active and quiet. We might have just caught the Phoenix cluster in a rare, brief phase where the black hole is temporarily dormant, allowing the gas to cool catastrophically. Or it could be that the gas in this particular cluster has properties that make it much more efficient at cooling than in other clusters. The Phoenix cluster is a unique laboratory. It is a case study in what happens when the cosmic thermostat breaks. It shows that under the right conditions, the giant, dormant galaxies at the hearts of clusters can roar back to life with a spectacular burst of creation. It forces us to refine our models of galaxy evolution and the complex relationship between a galaxy and its central monster. Number one, the cosmological principle itself may be the rule that is broken. The final object is not a single star or galaxy, it is the universe itself on the largest scales. The problem lies with the cosmological principle, the foundational assumption that the universe is homogeneous and isotropic. This principle underpins our entire standard model of cosmology. It allows us to apply the laws of physics uniformly across the cosmos and to make sense of observations like the cosmic expansion. But a growing body of evidence suggests this principle might be wrong. We have already seen two examples of this: the Hercules-Corona Borealis Great Wall and the huge LQG. These structures are simply too large to exist in a universe that is supposed to be smooth on large scales. They suggest that the distribution of matter is far lumpier than predicted. But there are other, more subtle anomalies. One comes from studies of the cosmic microwave background. The Planck satellite provided us with the most detailed map ever made of the CMB. While it is remarkably uniform, it has strange large-scale features that do not seem to be random. There is a hemispherical asymmetry where the temperature fluctuations seem to be slightly larger on one side of the sky than the other. There is also an axis of evil, a strange alignment of the largest features in the CMB with the plane of our solar system, which suggests a bizarre local influence on a cosmic signal or a fundamental preferred direction in the universe. Another line of evidence comes from mapping the motions of galaxies. Some studies suggest that there are large-scale book flows, where huge swathes of the universe are moving in a coherent direction that cannot be explained by the gravitational pull of known structures. This would also imply a preferred direction, violating the principle of isotropy. Even more recently, studies of distant quasars and radio galaxies have found alignments in their rotation axes over vast distances. It is as if galaxies billions of light years apart somehow know about each other and have aligned their spin, something that should not happen in a random isotropic universe. Each of these anomalies on its own could potentially be dismissed as a statistical fluke or a systematic error in the data. But taken together, they paint a concerning picture. They all hint at the same thing, that the universe is not the same in all directions. It may have a large-scale structure, a grain, or a preferred axis that we have failed to account for. If the cosmological principle is wrong, the implications are profound. Our calculations of the age of the universe, the amount of dark matter and dark energy, and the ultimate fate of the cosmos all rely on this assumption. A universe that is not homogeneous would require a new, more complex model of cosmology. It might mean that the laws of physics themselves are not perfectly uniform. It is the ultimate rule breaker. These massive objects and strange alignments are not just isolated curiosities. They are clues pointing towards a deeper and perhaps stranger reality than the one described in our textbooks. They are the cracks in the foundation of our understanding, and they hint at a new physics waiting to be discovered.